This is Jonathan Whitfield, Lab 5 Part 1 at-home video lab report. For this lab, I dropped a fast-falling object and a slow-falling object, analyzed it in Tracker, and modeled it in Python. For my fast-falling object, I videoed a full Nalgene water bottle and then analyzed it in Tracker. For my slow-falling object, I videoed a crumpled up piece of paper and then did the same. And then here's a quick overview of the momentum principle. Here is the graph of the slow falling object. Here's the fast falling object. Here's comparing them both. Something interesting I saw was it took just about twice as long for the crumpled piece of paper to fall the same distance as the water bottle. And I went to Python and modeled the slow object with just gravity affecting it, and this is my result. See, without drag it falls a lot faster compared to real life. And then this is it with drag. When you model it with drag, it's a much of a closer match. If you see my drag coefficient, it is very big. Means there's a lot of drag on the crumpled up piece of paper. For the fast object, the blue dots are the computer model, so an ideal situation with just gravity, and the reds my data from Tracker. So it's a pretty close match. And then when you do it with gravity and drag in Python, you can get it very close. And if you notice, the drag coefficient is a lot smaller than the drag coefficient for the piece of paper. So here we'll go and view these two. So this is the model of the water bottle with drag, and this is the piece of paper. You can see here by the arrow that there's a lot of drag acting on it. See some, and then so what does it mean? For the object that drops slowly, examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? So, to do that, go back to these. As you can see, both of these, they level out. The graphs become linear, which means they have reached terminal velocity. Same with the gravity and drag. They both become linear. So, under both models, they reach a terminal velocity. Then what if? For the object that drops slowly, use your models both with and without drag to examine the object's velocity as a function of time in the case where the object is thrown downward initially instead of dropped from rest. In this case, does the object reach a terminal velocity? Examine both models with and without drag. Compare the terminal velocities, if any, in this case with the case where the object is dropped from rest. See, in both my models, the object reaches a terminal velocity when the slope of the graphs become linear. In the model with gravity and drag, the object reaches terminal velocity much quicker than the model with just gravity. We can see that by looking at here, it doesn't reach terminal velocity until about maybe 0.7. Here, it reaches about maybe 0.3. So the drag causes it to reach terminal velocity much quicker. That is my lab report. Thanks for watching.